Good morning, everyone. Welcome to a new session of PR Teaching. Our team consists of three members. I'm Riya Johnson, and we have along with us Surya S Karun and Bodhi.S Dharman. Today, we'll be dealing a topic in chemistry. So, let's see a video to know today's topic.
Periodic table.
There's hydrogen and helium, then lithium, beryllium, or carbon everywhere. Nitrogen all through the air, and oxygen so you can breathe. Chlorine for your pretty teeth, neon to light up the sign. Sodium for salty times.
Magnesium.
Aluminium, silicon,
Phosphorus.
then sulfur, chlorine, and argon.
Potassium.
And calcium, so love goes strong.
Scandium.
Titanium, vanadium, and chromium, and manganese. This is the periodic table. No gas is stable. Halogens and alkali react aggressively. Period will see new outer shell will electrons are added, moving to the right. Iron is the 26th cobalt, nickel points again, copper, zinc, and gallium, germanium, and arsenic, selenium, and rhodium. Krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
Niobium.
molybdenum, technetium,
Ruthenium.
rhodium, palladium,
Silverware.
then cadmium and indium,
Tin cans.
antimony, then tellurium, and iodine, and xenon, and then cesium, and Rhodium is 56, and this is where the table splits. Well, anthemides have just begun. Cerium and praseodymium. Rhodium is next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Hafnium, tantalum, tungsten, and polonium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead that isn't for your tummy, polonium, astatine would not be yummy, radar, and cesium will last a little time, radium, then actinize at A. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. It will see new outer shell will electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, titanium, chromium, and nobelium, lawrencium, rutherfordium, sodium, borium, hesium, meitnerium, obsidian, mercurium, copernicium, natrium, ferrovium, pentium, livermorium, leptium, adamantium, and then we're done.
So, you might have understood what is our topic for today. Today, our topic is periodic table. The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students. It suggests new avenues of research to professionals, and it provides a succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemicals are not a random cluster of entities, but instead display trends and lie together in families. An awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of chemistry, that is, the chemical elements. In this unit, we will study the historical development of periodic table as it stands today and the modern periodic law. The objectives of learning today are: first, to appreciate how the concept of grouping elements in accordance to their properties led to the development of periodic table. Second, to understand the periodic law. Third, to understand the significance of atomic number and electronic configuration as the basis for periodic classification. And finally, classify elements into S, P, D, and F blocks and learn their main characteristics. So, why do we need to classify elements? We know by now that the elements are the basic unit of all types of matter. In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 114 elements are known. Of them, the recently discovered elements are man-made, and efforts to synthesize new elements are still continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and the innumerable compounds individually. To ease out this problem, scientists search for a systematic way to organize their knowledge by classifying the elements. Not only that, it would rationalize known chemical facts about elements, but even predict new ones for undertaking further study. So we'll see what were the earlier attempts for classification of elements. The earliest attempt to classify elements was in 1789 when Antoine Lavoisier grouped elements into metals and nonmetals. In 1807, John Dalton put forward atomic theory. This theory established that each element has a fixed atomic mass. This gave a sense of direction to the classification of elements. In 1829, German chemist Johann Dobereiner attempted to classify elements with similar properties into groups of three elements, and these groups were called triads. He suggested that in these triads, the atomic mass of element in the middle would be more or less equal to the mean of atomic masses of other two elements in the triad. An example of such a triad would be one containing lithium, sodium, and potassium. We know that atomic mass of lithium is 6.94 and that of potassium is 39.10. The element in the middle of the triad, that is sodium, has an atomic mass of 22.9, which is more or less equal to the mean of atomic masses of lithium and potassium. These are three sets of triads. So if you see, you will understand that if you add the atomic masses of lithium and sodium and divide it by 2, you will get the atomic mass of, if you add the atomic masses of lithium and potassium and divide it by 2, you will get the atomic mass of sodium. Similar is the case with calcium, strontium, barium, and chlorine, bromine, iodine. Now we'll see the limitations of Dobereiner's triad. All the elements known at that time couldn't be classified into triads, and only 4 triads were mentioned. First one was lithium, sodium, potassium. Second one was calcium, strontium, barium. Third one was chlorine, bromine, iodine. And the fourth one was sulfur, silurium, and tellurium. Then came law of octaves. English chemist John Alexander Newland in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weights and noted that every eighth element had properties similar to the first element. The relationship was just like every eighth note that resembles the first in octaves of music. Newland law of octaves seemed to be true only for elements up to calcium. Although his idea was not widely accepted at that time, he for his work was later awarded Davy Medal in 1887 by the Royal Society London. So we'll just see what Newland's law of octaves states. Newland's law of octaves states that when elements are arranged in the increasing order of their atomic masses, the periodicity in properties of two elements which have an interval of 7 elements in between them would be similar. This is the form of Newland's octave. So if you see, we'll understand that lithium, sodium, and potassium have similar properties, which are the repeating 8 elements for each set. The limitation of Newland's octave was that it was only up till calcium that the classification of elements is done. Now, I invite Surya to tell us about Mendeleev's periodic table. So, Surya, can you unmute?
Okay. Now we are going to deal with the most important milestone in the evolution of periodic table. It's none other than the Mendeleev's periodic table. As Mendeleev says, pleasures felt by there are only for yourselves. Work leaves a mark of long-lasting joy. Work is for others. Yes, the quote is right. The work he has done is a pathway for others. In 1869, a Russian chemist, inventor, and teacher named Dmitry Mendeleev formulated the periodic law. He used it to correct the properties of some already discovered elements and also to predict the properties of elements yet to be discovered. The Mendeleev's periodic table is mainly based on the two factors. That is, the periodic table of Mendeleev was discussed about the main two factors for classifying the elements. The first one is the atomic mass, and the second one is the similarity of chemical properties. According to the Mendeleev periodic law, the physical and chemical properties of elements are classified on the basis of atomic masses. You can see in the screen that there are alkali metals are classified according to the atomic masses and similarity of the chemical properties as lithium, sodium, potassium, rubidium, and cesium. And also, the halogens can be classified into fluorine, chlorine, bromine, and iodine. The same case was done with the inert gases as they were classified on the atomic masses and the similarity in chemical properties as helium, neon, argon, krypton, and xenon. The main point that we deals with the Mendeleev periodic law is that the physical and chemical properties of elements are classified on the basis of their atomic masses. The merits or the advantages of Mendeleev periodic table deals with the following aspects. The first one is elements are classified on more a fundamental basis of their atomic masses and properties. We have already seen it as the periodic law. Spaces were left vacant to accommodate the elements to be discovered in future. Future discussed elements should be the space are left for that. It could predict the properties of the elements, which helps the discovery of new elements. There was space for the new elements to be included. The inert gas elements discovered later could be placed in a separate group without disturbing the table. These were the main advantages that Mendeleev's periodic table deals with. So, in order to deal with this, we must bear in mind that when Mendeleev developed this periodic table, the chemists knew nothing about the internal structure of atom. At that time, the internal structure of atom was unaware to the chemists. Because of this, there were so many limitations to the Mendeleev's periodic table. The main limitations that deals with Mendeleev periodic tables are in the case of position of hydrogen. Here, the position of hydrogen was not correctly defined in the Mendeleev periodic table. That is, the position of hydrogen was placed in group 1, although its properties were similar to the group 1 elements and also to the group 7 elements. The group 1 elements are usually the alkali metals and the group 7 elements are usually the halogens. So, Mendeleev's periodic table does not give a correct definition or position to hydrogen. The second limitations that deals with Mendeleev periodic table is grouping of some elements. Some elements cannot be grouped according to Mendeleev periodic table in accordance with their similarities, while some dissimilar elements are grouped together in this periodic table. Thus, the position of these elements was not justified. For example, let us consider the example of cobalt and nickel. Cobalt was placed before nickel, and copper and mercury are similar in their properties but were separately placed. Copper was placed in group 1, although copper does not have resembled the properties with the group 1 alkali metals. And the third limitations that lie in the periodic table of Mendeleev was the isotopes. As we all know, isotopes are the atoms of same elements having different atomic masses and but same atomic number. So Let us consider the isotopes of hydrogen. As we all know, hydrogen has three isotopes: protium, deuterium, and tritium, with atomic masses 1, 2, and 3 respectively. According to Mendeleev periodic table, these should be placed at three separate places. But however, isotopes have not been separated places in the periodic table. So Mendeleev could not explain the isotopic position of hydrogen and other elements. The last but not the least limitation of Mendeleev periodic table is the anomalous pairs. In certain pairs of elements like argon and krypton, or else like cobalt and nickel, or like tellurium and iodine, the arrangement was not just justified or satisfied. For example, argon was placed before potassium, whereas its atomic mass is more than that of potassium. So, an anomalous pair of behavior was shown in the Mendeleev periodic table, and it was not justified according to the periodic law. So, we all know that these limitations should be wiped up or wiped out from the periodic table, and thus arise the modern periodic table proposed by Moseley, or it is always known as Moseley's periodic table that we have found today. Using atomic numbers instead of atomic masses as the organizing principle was first proposed by British chemist Henry Moseley in 1913, and it solved an anomalous that seems in Mendeleev's periodic table. The modern periodic table of Moseley almost wiped out all the limitations that were put forward in the Mendeleev periodic table. At that time, we have got many properties and many theories about the internal atomic structure that would make easy for Moseley to handle with the Mendeleev's periodic table. So, according to Moseley, the modern periodic law was just redefined as the properties of elements are the periodic functions of their atomic number and not of atomic mass. That is, there should be a difference in the Mendeleev periodic table, as there is the properties of elements are the periodic functions of atomic masses in Mendeleev's periodic table, but in modern periodic law proposed by Moseley was the properties of elements are the periodic functions of their atomic masses, not but atomic number. Okay, so we can see that the hydrogen's isotopes are being clearly defined in the modern periodic table. In the modern periodic table, groups and periods are defined as groups, the vertical columns in the periodic table, and it is 18 number. On the case of periods, it was been defined as the horizontal rows in the periodic table, and is daily the 7 in numbers. So there are 18 groups and 7 periods in the modern periodic law or modern periodic table proposed by Moseley. So in the modern periodic table, again the groups are classified into two, that is into subgroup A and subgroup B. It is none other than the subgroup A represents the representative elements, that is the topmost elements in the periodic table, and in the subgroup B position consists of the transition elements. You all know that the transition elements were classified into the long periodic table at the last position of the periodic table. Okay, so the subgroup A, the representative elements, was classified into further as S block elements and P block elements. Then the transition elements, which was placed later before in the periodic table as D block and F block. So we have now seen the long form of periodic table proposed by modern periodic table, or known as Henry Moseley's proposed modern periodic table as the follows. It mainly deals with the S block elements, the P block elements, the D block and the F block, and named as lanthanides, actinides, X block, P block and D block. So it's all about Mendeleev's periodic table and modern periodic table proposed by Moseley. And now I am handovering the session to Bodhi.S.
Hello everyone. Now we are going to discuss about classification of periodic table. The periodic table is divided into four blocks, mainly the S block, P block, D block and F block. First we are going to discuss about the S block. The elements of group 1, that is also called alkali metals, and group 2 alkaline earth metals, which have ns1 and ns2 outermost electronic configuration, belong to the s block elements. They are all reactive metals with low ionization enthalpies. They lose the outermost electron readily to form 1 plus ion in the case of alkali metals, or 2 plus ion in the case of alkaline earth metals. The metallic character and the reactivity increases as we go down the group. Because of high reactivity, they are never found pure in nature. The compounds of the S block elements, with the exception of those of lithium and beryllium, are predominantly ionic. Now we are going to discuss about the P block elements. The P block elements comprise those belonging to group 13 to 18, and these together with the S block elements are called the representative elements or main group elements. The outermost electronic configuration varies from Ns to Nb1 to Ns to Np6 in each period. At the end of each period is a noble gas element with a closed valence shell Ns to Np6 configuration. All the orbitals in the valence shell of the noble gases are completely filled by electrons, and it is very difficult to alter this stable arrangement by the addition or removal of electrons. The noble gases thus exhibit very low chemical reactivity,
Bodhi,
preceding the yes,
I cannot see your video. Now I can see.
okay, okay. Then the non-metallic character increases as we move from left to right across a period, and metallic character increases as we go down the group. Then we are going to discuss about d block elements. Elements in which the d orbitals are completely filled are called the d block elements. General electronic configuration is n-1 d 1 to 10 ns 1 to 2. Their properties are: it shows catalytic properties, it forms colored ions, shows paramagnetic properties, it forms complexes. They are often referred to as transition metals as they are placed between metals and non-metals, and also due to their characteristic feature. Now we are going to discuss about F block elements. Elements in which the F orbital is completely filled are called the F block elements. General electronic configuration is Ns2 N-1 D2 0 to 1 N-2 F2 1 to 10. Inner transition metals are known as F block elements. They have incomplete d orbital electronic configuration in their normal state and in their oxidation state. They are generally radioactive. Now we are going to discuss about trends in physical properties. They are atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, electronegativity, oxidation states, chemical reactivity. First, atomic radius. The atomic size generally decreases across a period as for the elements of the second period. It is because within the period, the outer electrons are in the same valence shell and the effective nuclear increases as the atomic number increases. This results in increased attraction between nucleus and the electron. Atomic radius decreases from left to right as principal quantum number increases. It also increases down a group as the number of shells increases. Then we are going to discuss about ionic radius. The removal of an electron from an atom results in the formation of a cation, whereas gain of an electron leads to an anion. A cation is always smaller than its parent atom, while a anion is always greater to its parent atom. This is due to electron-electron repulsion. Isoelectronic species are those species which have two or more species with the same number of atoms, same number of valence electrons, and same structure, regardless of the nature of elements involved. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. The last one is ionization enthalpy, a quantitative measure of the tendency of an element to lose electron is given by ionization enthalpy. It represents the energy required to remove an electron from an isolated gaseous atom in its ground state. In other words, the first ionization enthalpy for an is element X is the enthalpy change delta H for the reactant. X gives X plus electrons. Energy is always required to remove electrons from an atom and hence ionization enthalpies are always positive. So let's conclude today's session. Hope all of you have understand today's session. Have a nice day.